Okay. Okay, just okay. So I just want to ask you actually, do you see a good quality of the PowerPoint?
Yes.
Yes.
Okay, that's good. Okay, so let's continue. We said, as we said in the first session, in the first hour, we said that we are going to talk about matrices. Matrices is just a mathematical construct. It's an array of numbers placed in rows and in columns. For example, here we can see that the matrix shown here, it has m rows and n columns, and any entry aij it's in the ith row and jth column. So the second index, it denotes the column. Then we have the matrix notation. It can be a vector, such as the A and B, which are shown here. We can define a diagonal matrix is a matrix where all the entries that are not on the diagonal are equal to 0. Okay, so if everything is 0, with only the diagonal terms non-zero, we call this the diagonal matrix. In the first hour, we give an example how it can look like. Two matrices are equal if they are the same size and if the corresponding entries are equal. Okay, so a matrix 3 by 3, it can never be equal to a matrix that is 2 by 2, okay, because the size should be the same, and also all the entries, one-to-one correspondence, should be equal to each other. Matrices, okay, for example, here we have an example of a square matrix, which is 3 by 3, which is A11, A21, A31, and the entries which are A11, A22, and ANN, they are considered the diagonal terms of the matrix. You can find, sometimes we find some usage of partitioning the matrices. To partition a matrix, we can carefully separating a large matrix by drawing horizontal and vertical lines, as it is shown in this slide. Okay. So, for example, the column that carries A11 and A21, it can be denoted just as capital A11. Okay. And then you see this 2 by 2 matrix appearing on the right side, top right side of the large matrix. We can denote this one as A12 and so on. So partitioning is something that we can use. Actually, partitioning is a very important tool that we can use, and it's often used to reduce the computational complexity. If the original matrix is huge, we can partition it into smaller parts, and then the computational complexity, it can decrease. Because sometimes some operation, they don't, because for some operations, different sections of the same matrix, they are not coupled at all. If they are not coupled, and I have a couple of examples which I can provide for you, if they are not coupled, then it's better to partition it, do the operations at a lower dimension, and then merge them back again. Because computational complexity of a matrix, often it is n squared. Okay? A matrix which is 5 by 5 sometimes might need 5 square operations, which is 25. But a matrix which is 10 by 10, it needs 10 square, which is 100 operations. And with this regard, we can count how many calculations we need to do for a specific size matrix. We can define zero matrices, which are matrices or vectors where all elements are zero. We can define identity matrices. Identity matrix is a matrix which is a diagonal one, and all diagonal terms are equal to 1. As we can see here, so we have I3, which is a 3 by 3 matrix, I2, which is a 2 by 2 matrix, and any vector that is multiplied by an identity matrix, it does not change. Okay. Then we can define different operations with matrices, such as the matrix arithmetics, where the simplest one would be addition and subtraction. The definition of addition and subtraction, we can see it here in this slide. A matrix A and B, adding them is equal to each element of A, adding them to each element of B, 1 to 1. And if we have two matrices of different size, we can never add them. Okay, so the addition is not defined. So if you come to the exam and you are given two matrices that don't have the same size, don't add them. Okay. Or you can simply state, report, that the addition is not defined. Now again, the addition of these two matrices, we can see it also here. So element-wise, element-to-element addition, as shown here. Then we can also define the scalar multiplication of a matrix. Now, a matrix is like a more complex term than a vector. Okay, like vector quantities is different, and scalar quantities are different. Matriz scalare janë thjesht numër. Matriz vectoriale kanë dhe drejtim. So multiplying a matrix with a scalar, in this case a constant c, it is also a defined operation. And we're going to see this one as a very important step in the future weeks. Now, matrix of arithmetics. We have here two matrices A and B, and we can simply calculate here A minus B, B minus A. For example, what is, let me answer this one, what is the, let's assume that A plus B is a matrix C. So what is C 2, 3? Element, if C is equal to A plus B. So
12.
that's 12, that's correct. Okay, so we add those, and then the C11. What is C11?
10.
Exactly, okay, so this is how we add them, right? And then if we want to find, for example, 2A minus 3B, if you want to find the element 2, 4, we get 2 times 0, 2, 4, right? So we have to find second row, fourth column. So we have for A, 2 times 0 is 0, minus 3 times 7 is minus 21, okay? So this is how the addition and subtraction is defined. At the same time, if we put together, if we multiply several matrices, we multiply them with several constants, and then we add those, this is defined as a linear combination of these matrices or of these vectors, okay? And a linear combination, let's not forget what linear means. Linear means that any variable or any quantity is to the power 1, okay? So if you have x plus y plus z, it's a linear combination because x, y, and z, they are all to the power 1. But if you have x squared plus y cubed plus z to the power 4, this is not a linear relation or linear combination, okay? So let's keep this in mind. Then we can also define, because this is a little simpler, we can simply multiply a vector with another vector, but it's best if it is a row times a column. In order for the multiplication to be defined, we need the number of columns in the first vector to be equal to the number of rows in the second vector. For example, the vector A, which is shown here, which is a row, the dimension, it is 1 by n. Okay, 1 by n, it means one row, n columns. The dimension of vector B is n by 1. Okay, so it has n rows and a single column. So it looks like the number of columns of A is n, the number of rows of B is n, so we can define the multiplication is defined. Now, this is the matrix multiplication. Now, this definition is just giving a little detail of how we multiply, how we obtain, when we multiply two matrices, A times B, which would be equal to C, how we can obtain the second row of C, for example, or how we can obtain the second column of C. This is what this slide is about. And now, when we do the arithmetics, we, to find, imagine for a moment, that we need to find CIK, okay? CIK, you can see that AIJ, we multiply it with BJK. Now, here, we're going to do an example on the board, but I want you to remember that anytime you have the same index appearing twice, that means that you are going to add over that element, okay? So, you have AIJ times BJK, you are going to add over J. But what does this mean for you? If A and B are 3 by 3 matrices, that means that J is going to be 1, 2, and 3. Okay? Keep this in mind. You can take a note when you solve the example. We'll understand it. Here we have matrix A and B. So, what is the dimension of the product of A times B? What is the result matrix? We don't know this yet, actually. But the A itself, it is 2 by 4. B is 4 by 3. For the moment, what we have learned so far is just that this multiplication of A times B, it is defined. We can multiply those, okay? We don't know yet what the dimension is going to be, but we're going to check this one. Then we have also B times A. B times A, this means that we multiply a matrix which is 4 by 3, which is a matrix which is 2 by 4. In this case, the multiplication of B times A is simply not defined at all, okay? But A times B, it is. Now, let's do this one on the board actually, but I need to, let's see this one. Stop presenting the screen. Okay, we can go back. I just want to see what this matrix looked like. Okay. So the multiplication is defined as, how is the board? Does the board looks good?
Yes.
Yes.
Okay, so because the eraser is not perfect, unfortunately, but let me try to make it slightly better. Here we go. For example, any matrix A, which is n by n, we multiply this one with a matrix B, which is n times k. This is going to be equal to a matrix which is equal to m times k. So this is how multiplication works. So these two indices should be equal, and the answer is going to have dimensions like these. Okay. Now let's see. If you go over the slide, we look at, we notice that this is capital C, okay, and this is a matrix. Let's denote it like this. This is a matrix. This is also a matrix. Now we looked at the Cij, that we are at Cik. This was equal to Aij times Bjk. Okay. So this is what we saw together in the slide, in the PowerPoint slide, and in principle, anytime you see this index twice, what this is really doing, this is, we are summing over the value of j, which is going to be equal from 1 to n, okay? Let me add this n, because this is the, how many times this will appear. And this is going to be the Aij times Bjk, which means that this is going to be this A1, no, this is I1 times B1k plus AI2 times B2k plus AI3 times B3k. Okay, so I think it's obvious that we are just changing the value of j, but keeping the other two elements equal. Okay, so often you're going to see this, but in principle you are doing this. Okay, so because j, any number that appears twice, you are summing over it. That's how we can see. Now let me have a look at the, or actually we can define, let's define two matrices that look like this. 1 minus 1, 2, 3, 2, 0, 1, minus 2, 4. Okay, this is a 3 by 3 matrix, and let's multiply this one with 1, 7, minus 1, 2, 3, minus 5, 1, 1, 1. Okay, so here we have two matrices, and we want to multiply those. So right away, let's figure out what is, when we multiply these, what is, this is A, matrix A, this is matrix B, And we need to find out what is matrix C. Well, C, what is the dimension of C? What should it be? What is the dimension of C?
3 by 3.
Exactly. This is going to be 3 by 3. That's good. Let's try to identify what is C11. Okay? C11, it is defined by definition. C11, it is the first row of A times the first column of B. Okay? This is defined like this: 1 minus 1, 2 times 1, 2, 1. Right? This is it. Another example. C23. What is C23? Is the second row of A. What is second row of A? It's
320.
Thank you. Okay, times what? The third row of B.
-1, -5, and 1.
Minus 1, minus 5, 1, of course. Okay. And let's solve the first one. What was this? This is 1 times 1. So this is 1, 1 plus minus 1, 2, minus 1, 2 plus 2, 1. What is this equal to? 1 minus 2 is minus 1, plus 2 is 1, okay? So this is 1, this is C11, this is this element. Then, we're looking for C23, we have the following. This is going to be equal to 3 times minus 1, plus 2 times minus 5, plus 0 times 1. Plus 0 times 1. This is equal to 3 minus, this is minus 3, minus 10, minus 13. Okay, so here we have minus 13. Okay, so this is how we do this. Okay, so each element here that we are looking for, okay, the CIK, this is how we are writing this, right? And we are summing over these elements. Okay, so we are considering, we are keeping the row the same. Okay, so we did it. Here we kept the row the same, we kept the column the same, but we are considering all elements. Now, how would we write this differently? This would be written like this: A, we write this one, A 2J times B J3, right? Based on the definition up there. So this is what we are doing here. I'm writing the same expression. But then this will be equal to A 2, 1, B13, because this is the case when J is equal to 1, right? Then we have plus A 2, B23. This is the case when J is equal to 2. Okay? And then plus A 23, B33. This is the case when J is equal to 3. So in principle, we are summing over all the J's. The same way that we use the summation notation. And the summation notation, the sum, we use this capital sigma. Okay? This capital sigma, we sum from the smallest value to the largest. And in principle, this is what we have here and here. Okay? Here and here. So this is how we do this multiplication of these matrices. And now, let's check again. Yeah, we can follow the pattern again with multiply these values. For example, let's find this element here. This element here, which is C22, it should include second row with second column. What happens then is that we need to look at this row. Okay, this is a failure. Let's find another pen. So we have this row, we multiply with this column, and we should get the following. 3 times 7 is 21, 21 plus 6 is 27, 27 is 0.
What is
Is it 27? Okay. Okay. Then we write something similar. We say that, let's find this one. What is this element here? This element is the second row of A times the first column of C, of B, so we have these two. So we match each element here and here, we get 3, plus 4, 7, 7. Okay, then we need to find, we can find this element, which is going to be this row times this column, so it's this row now. 4 minus 4, it's 1, right? I get a 1 here, then this is like this. Let's try, we can try to identify this number here, which is going to be the first row here times the second column. You can also notice that this element here is the intersection, this is a question mark, okay? This is the intersection of this row with this column, so it would be easily how to track it down. We have 7 minus 3 is 4, plus 2, 6, okay? And so on. Okay, so this is how we define the matrix multiplication. And then one question would be this one. Assuming that this is A, this is the matrix A, and we have another vector, another matrix, let's call it this way. Let's have a matrix A1, which is equal to 1, 1 minus 1, 2, 2 minus 4. This is A1. And you can find what is A times A1 is equal to a matrix D. What is the dimension D?
3 by 2.
Exactly, because this is 3 by 2, okay? So this is 3 by 3 times 3 by 2. This is going to be a matrix 3 by 2. And what is A1 times A? A1, it's a matrix which is 3 by 2, and we want to multiply it with a matrix A, which is 3 by 3.
It will be 3 by 3.
Let's not forget the definition of the multiplication of two matrices, which is here.
It cannot be defined.
It's not defined.
That's true. Okay, so this is not defined because the number of columns here is not equal to the number of rows. We cannot match every pair of numbers. So here we just say not defined. Okay, so we cannot. Nobody can find it. It's not defined yet. Okay, maybe someone in the future might show up. And yeah. So this is how we can follow, or this is how we do the matrix multiplication. Now let's see, we can have another look. Now. Okay, so again, we come back to the same slide. So we talk about the matrix arithmetics, simple matrix arithmetics. We can compute A times B and B times A. In this case, it looks to me, what is the dimension of B times A? Can you answer this?
It is not defined.
That's correct. Okay, it's not defined. So we don't always find anything that it is asked, but we look even whether it is something is defined or not. So this is something we have to be careful. This is C and D, they are 3 by 3, both of them. I guess both C times D and D times C, they are both defined, so we can do it easily. Then continuing with I think we talked about this slide, which says that whenever we multiply two matrices, the ith row of AB is the ith row of A times B, okay? And the jth column of AB is all A times J. In fact, what we wrote on the board, it was more like this. Any element, for example, element of C45, okay? C45 is the fourth row of A times the fifth column of B, right? So this is is how we can read this whole slide. For example, how can we compute the second row of AB? How can we compute the second row of AB? We get the second row of A, we multiply with the whole B. That's how we do it. Similarly, to get the third column of AB, we multiply the whole A with the third column of B. Okay? And we get the indications of how to do that in this slide, and we apply it here. Now, yeah, okay, so we repeat it again, what it was on the previous slide. Then here, A times B, this looks like a special case, but it really isn't, because A is the matrix, B is a column. And here we just say that A times B is equal to the B1, which in this case times the C1, which is the first column of A. Okay. The way the multiplication will go forth is that A11 will be multiplied with B1. A21 will be multiplied with B1 again, right? So the first element on the first column of A, they will go like that. So in principle, multiplication of A and B will be such that B1 will multiply the first column of A, B2 will multiply the second column of A, B3 will multiply the third column of A, and so on. And in principle, the result, it will be a linear combination of the columns of A. Okay. Okay, and actually, what you see in this slide, if you take a note here, maybe right now you don't understand it very well, but when we solve systems of linear equations, the linear combination of columns have a very essential meaning, which we'll provide this in detail in the future weeks. Let's continue. We have some also associative laws and some distributive laws, as shown here in the slide. Adding two matrices, three matrices, we can add the first two, and it is equivalent with adding the second and the third first, and then adding the first one. So they are all equivalent. Then lambda is a scalar quantity, and the product of two matrices A, B, you multiply them by a scalar quantity lambda. It is the same as lambda times A times B, and this is also equal to A times lambda B. As you can see, we can see on the slide. You can see the third property, multiplication of three matrices, A times B, then multiplied by C. It is equivalent to multiply the A with the product of BC. We have distributive laws, as they are shown here on the slide. We talked about zero matrices. We talked about identity matrices, where all the diagonal elements were 1, and the non-diagonal terms were 0. For example, here, Aij is 0, as long as J and I are different from each other. Here, there is an important property of matrices. Some matrices, not all, have an inverse. Inverse, it is defined as A times B is equal to identity matrix. B, in this case, would be called the inverse of A. And the inverse matrices, they are unique, which means that for any matrix A, if the inverse exists, it's only one. You cannot calculate two different matrices, which are both inverses of the same matrix. This is what this slide is talking about. And we have also some properties, such as the inverse of a matrix is the same original matrix. This can be proven, it's easily proven. And what is also interesting is the third identity here, which is that A times B, the inverse of A times B is equal to B inverse times A inverse. Okay? And actually, the proof of the last identity, you can intuitively read on the right side of the slide. Imagine for a moment, you have the matrix AB, you multiply it with B inverse A inverse. The way they multiply is that we want the identity matrix in the end. But if you multiply B and B inverse the way that they are shown over there, you get the identity, and then you will be left with A times A inverse. Okay, sorry, I have a problem with my monitor, but I think everything will be back in shape. Okay, you can see also the second identity, which states that any constant C times A, the inverse of that is going to be 1 over C times A inverse. Well, I still have this problem. Okay, problem solved. We move ahead. Inverses. I think we talked about this one. So if AB is equal to AC, then B is equal to C. That's the property of the matrices. Now I guess, okay, so we have also to discuss about the transpose. The transpose of a matrix, it is defined as taking the, let me call it, diagonal mirror effect of a specific matrix. It's not the most technical term that I said today, diagonal mirror effect, but you can also call that the rows of A becomes columns of A, and also the columns of A becomes the rows of A. Now, this is the transpose. This is how transpose looks like. You can compare the two matrices on the right side. You see, for example, where A12 is initially, and when we calculate the transpose, A12 exchanges places with A21. We can define also the trace. This is also an interesting property. Trace is defined as the summation of the diagonal terms of a square matrix. Okay. So in a 3 by 3 matrix, we just trace is equal to the addition of these 3 elements on the diagonal. Trace has also some is invariant under cyclic permutations when we multiply 4 or more matrices. So if you have matrix A, B, C, D, if you pick out the A and you put it at the end, and you calculate now B matrix times C matrix times D times A, we get the result, and the trace, it's invariant. Okay, it's an interesting property. Now, what is interesting is that the trace, the determinant of a matrix, they're not just numbers. It's strange. I mean, I always get impressed because all of these, they represent something which is also in space. Okay, it also represents a feature of the space, or a feature of the volume of the space. So a 3 by 3 matrix, imagine for a moment, in a 3 by 3 matrix, each column, it corresponds to 3 vectors, okay? Now, determinant of a matrix, it's in fact the volume that these 3 vectors occupy in the space. Trace has also impressive properties, which we're going to see them later in the future weeks. But just keep in mind that these mathematical constructs, which is array of numbers put in rows and columns, they also have very impressive properties. So personally, I don't understand why trace is invariable here. It can be proven, but one further step that any one of you can do to get a better understanding of what is happening in geometrical space is to intuitively expect or understand why trace is independent of this cyclic permutation, or why is it invariant. Now, for example, here we have, let's have a look. What is the trace of matrix C? Who can answer this? Matrix C is a square matrix, and here, this is the definition of a trace. Trace is A11 plus A22 plus A33 plus A44 and so on. This happens only for square matrices. Let's see here. What is the trace of A? First of all, trace of A, it does not exist because A is not square. If it was square, we could have the chance that the 1 plus 5 would be 6, but no. B, we cannot find the trace of B because B is also not square, but we can find the trace of C, and in this case, the trace of C will be it will be plus 3. Because when we have minus 5 plus 8, we get plus 3. This is the trace, okay? Transpose of A, we can define it, and the transpose of A is 2 by 4. It has 2 rows and 4 columns. If we want to calculate the transpose, it would be 4 rows and 2 columns. It would be slightly different. I think this is all actually regarding all of these elements, and so we just did. Say it again.
Can I do quick?
Sure.
So the trace is diagonal.
You know, I'm sorry, but I cannot understand. Can you?
Like, what should we put the trace on matrix? I don't understand.
Can you write this? I apologize. I don't know what was the fault here. Whether it's your microphone or my. Can you write your question or your comment in the chat session? The shortening to that's true. So the trace is just the sum of diagonal elements. But this works, or it is defined only for square matrices. Yeah. For example, that 5, this matrix C, trace is just 3, okay? What we see here in the slide. Wait a second. Am I sharing my screen? I think I am. Yeah, okay. Yes. Okay, so this is actually what I want to cover mostly for today, which is we just gave a review. Not a review, just we went over what we are going to do this semester, what matrices are, what are the major topics we are going to cover, and we just gave also a general introduction. Do you have any question for today?
No.
Okay.
No.
If you
Professor,
yes.